merge sort and how you can use master theorem to solve recurrences. Any questions? Okay, so let's talk about the next thing I want to talk about is actually quicksort. But before that, let's have a quick discussion of recurrences of a different form and what they lead to, right? So the Fibonacci series is something that you all know about. So Fibonacci, if n equal to 0, return 0. If n equal to 1, return 1. Otherwise, return the sum of the two previous Fibonacci numbers, right? So this is a recursive formulation of Fibonacci. So there is, of course, an iterative formulation using an array, right? So we can, but what we are concerned about is the complexity of this recursive formulation. And you can see that there is a constant cost, right? So I call it 3, but it's just a constant, right? So there's a constant cost of executing the body, and then you have two recursive calls on n minus 1 and n minus 2. So t of n is t of n minus 1 plus t of n minus 2 plus some constant, okay? And if you try to write this down, once again, when I say if you have a more complex recurrence, you are going to guess. You don't guess from vacuum. The way you guess is by basically writing out the recursion tree and then seeing what happens in the first few levels, right? 2 or 3 levels, and then from that you can guess a closed form solution, and then you can substitute and check, which is really the induction proof, right? So in this case, Fn calls Fn minus 1 and Fn minus 2, Fn minus 2 and Fn minus 3, and so on. Okay, and you can see that the depth of this tree is going to be n, right? Therefore, you can see that its width should be of the order of 2 to the power n, right? So this is an exponential algorithm, right? So once again, you can see that at a high level, the way we are thinking about is no different from here, right? So we are still drawing out the recursion tree and then talking about the cost at each level, right? And so we do the same thing here, and we say that we have of the order of 2 to the power n leaves, and therefore they are therefore the cost of this recursive definition is 2 to the power n. Okay. So of course you can also write a much more efficient version of Fibonacci using an array to remember previously computed values of our previous Fibonacci numbers, right? So then you have a simple iterative formulation with, you say, f of I is f of I minus 1 plus f of I minus 2. So what is the complexity of this algorithm? It's obviously linear, right? So we just have one loop, right? And the loop goes, it's linear in size n. Therefore, this whole thing is going to take linear time, except that there is a catch. Fibonacci numbers grow very fast. So you can't, when we do, so we are doing addition, right? And we tend to assume that addition takes constant time, right? So this is reasonable as long as you are working with numbers which have a constant number of bits, right? So obviously our experience with computers is that we have 32-bit machines and 64-bit machines, so it's constant, right? 32 or 64. But for Fibonacci numbers, you have a large number of bits. So for instance, if the nth Fibonacci number needs about 0.7n bits, right? So if you want, the 1000th Fibonacci number, that needs 700 bits, right? So clearly, you can't assume that's going to be less than 64, right? So, so the calculation that this takes only constant time, you need to be careful because some of the operations involved may actually take more time than may not even any longer be constant time, right? So, so if you factor that in, then you'll find that, oh, okay, so it's going to be actually, how long does it take to add two n bits numbers? What is the complexity of an algorithm that adds two n bit numbers?
Linear.
Order of n, right? So it's linear. So, so you can say that each step here is going to be O of n, right? So therefore, the actual complexity of this is of O of n squared, right? So that's the, so there is, of course, there is a way to do this faster, it seems. So there is a method given in your textbook that can calculate it not in n squared time, but actually in n log n time. Okay. So again, you can think of the technique we used in exponentiation, right? So where instead of taking O of n, instead of having to do O of n multiplication to exponent, we did O of log n multiplication. Right? The same way, there is, instead of an n factor, you replace that by log n factor here. Right? So some idea very similar to how we did exponentiation will give you this. Right? So, okay, so that's a quick side discussion on Fibonacci, also giving you some idea that, in fact, your recurrence relation, right? You got to be careful, and sometimes, even though two recurrence relations may look somewhat similar, right? 2 times t of n by 2, right? In one case, you had 2 times t of n by 2, and that was an n log n algorithm, and the other one was t of n minus 1. And this is an exponential algorithm, right? So it seems like 2 times 2t, and this also seems like 2t, but you really have to divide n by some number, right? If you just take a constant off, that's no good. You'll end up with the exponential algorithm in the recursive case. You just took off a constant. Okay, you just subtracted a constant, you're dividing by a constant. So that's why. Okay, so now let's look at quicksort, right? So, so we looked at merge sort, so let's look at quicksort. And I presume all of you, again, are familiar with quicksort, even though you may or may not fully remember it at this point, right? So quicksort is kind of similar to merge sort, right? In the sense that you again divide the list into 2 parts, and then sort them, and then you combine them, right? So this is a so we start there, and then combine. Right? So we start this about both merge sort and quick sort. Right? So they are both divide and conquer algorithms that have very similar stuff to divide the list into two. Probably sort them and combine. Okay. So what's the main difference? In the case of merge sort, you do know what essentially a division, right? We are not smart about division, we just count, right? And then we pay the price at combination time. We need to actually compare them one by one, and at that time we pay the price. In the case of quick sort, we are smart about how we divide. Okay, so we are going to spend the effort at division time. At the time of combining, we are not going to be able to. How do we do that? What we do is, the way we divide it is, we divide it so that all the elements in one half are bigger than all the elements in the other half. Right? So the first list here is going to contain elements, all of which are smaller than every element in the second half. And once you have done that, after sorting, you don't have to do any work. You can just combine them, right? Concatenate them, and that's it. So that's what we're going to do. We're going to use this function called partition, which is going to divide up the array into two parts, such that the first part of the array contains elements, all of which are less than the second part of the array. Okay? So, details. Quick sort takes three parameters: the array that you want to sort, and it sorts the part of the array from L through H, right, inclusive. So it sorts AL through AH. Okay, so that's the purpose. And the first step is L greater than or equal to H, which means that the array that you want to sort contains, 0 or 1 elements. Okay, so well, there's nothing to do if the array doesn't have. If the array has 1 element or less, well, there's nothing to do. You just return it. Right? Otherwise, you're going to, it has at least 2 elements, right? So at that point, you're going to divide it into 2 parts, and then you're going to sort them recursively. And then, since the combination step is, things are already in the right order, we don't have to do any of the combination steps. So the quick sort ends after the 2 recursive calls itself. Right? Okay. So now, what does partition do? Partition basically rearranges the elements in this part of the array, AL through H, okay? And it gives you some delimiters. Okay, so let's try to understand exactly what partition does, and then we'll come back to quick sort. Okay? So what partition does is it picks a pivot element. Right? So a pivot element is one such that everything less than the pivot will go on the left side, everything greater than the pivot will go to the right side, and then the pivot itself will come right in the middle. Okay? So we're going to select the pivot. Okay? So, so notice that this K is not the pivot value, it's actually the position, location of the pivot. Right? So you just pick. So essentially, typically what you would do is you would pick a random value between L and H. Right? So if you pick a random value between L and H, that could be the select pivot function, just a random number between L and H. So the pivot location is K, the pivot value is A of K. Okay? And then what you do is, this is just the mechanics of bookkeeping. What you're going to do is you're going to put, temporarily store the pivot in the, last position, right? Swap AHK, what it's going to do is it's going to swap the values stored at location H and location K. And notice that H is the last position. So you're just going to, put the, remember the pivot in the last position so that it's just conveniently there, right? And then what you're going to do is you're going to, so this is location L plus 1, right? This is H minus 1, and so on, right? So after this swap has been done, the pivot value has been put in the location, the last location, right? So you know that P is sitting here. Okay? So now what we are going to do is we are going to have 2 pointers, right? I and J. Okay? So what we're going to do is this pointer I is going to go left to right, okay? And this pointer is going to go from right to left, okay? And they will meet in the middle, and that's where the partition is formed, okay? So let's go through this more carefully. So you start with I equals L minus 1, so I guess I is here, right? And J is here. So first thing you do is you increment I, right? So let's take our elements. Okay, so let's say this is our input, right? To partition, okay? So, and let's say we have to select the pivot. Let's say the K, let's say happens to be 7, right? So we get K to be 7, and then we swap. So let's take K to be 4, right? So we are going to swap these two. So 8 and 4 are going to be swapped. And so this is the pivot P equals 4. Okay? So now we set I equals L minus 1, so I is here. And J is equal to H. So that is going to be J, right? So now I plus plus, and we are going to do this, right? So we're going to increment I, and so it's going to become here, right? And we compare A of I less than P. Is 10 less than 4? Let me describe this more clearly, right? Compare that. Is it less? No, right? So the loop is going to, you're going to get off this loop, right? And remember that I has already been advanced, because before the first thing you do in the loop is you advance I. Right? So I is positioned there. Now you do J minus minus, right? So again, you do J minus minus first, right? So we're going to, right? And we check if A of J is greater than P. Right? So 8 is greater than 4. So we're going to continue in the loop. So we're going to come back and decrement J again. So J now go here, right? And then we check is A of J greater than P. Is 1 greater than 4? No, right? So at this point, so that loop breaks. And now we check if I is greater than or equal to J. Okay, that means we start I to the left and J to the right, right? So if I becomes greater than J, that means they have crossed over. That means you're done with the partition, okay? But if it is less, then you know that I was pointing to an element that happens to be greater than the pivot. So what do you want? We want everything to the left to be less than the pivot, and everything to the right to be greater than the pivot. Right? So now what we have done in this loop is we have identified some element in the left partition which is greater than the pivot. So we need to move it out. Similarly, when we get out of this loop, we have found some element in the right partition which happens to be less than the pivot. So it has to be, that means it is in the wrong place. Right? So now we have I and j both pointing to elements that are out of place. So what you need to do is you need to swap them. Right? If you swap them, then you would be okay. Right? So that's what you're doing, positioning I and j are swapped. So this will become, 10 will become 1, and 1 will become 10. Okay? And then we go back to that loop. Right? So now you're going to again increment I. Okay? And once again you have an element that in this left partition that's greater than the pivot. So you're going to stop the scan. Then you're going to move this to the left. And once again you have an element that is less than the pivot on the right half, on the right partition, right? So once again you have to swap. So you're going to swap 7 and 2. Right? So again go back to the loop, then advance I, right? So you have an element that is less, okay? That is less than the pivot, so it's okay, it's in place. So you need to advance I further. Okay? Now you have an element which is greater than the pivot, so you're going to get out of the loop. Okay? And then you're going to go here, and you're going to do j minus minus. So j is going to point to this, right? And then that condition now is not going to be satisfied, right? A of j is not greater than p, so you're going to come out. But now I and j have crossed over, so you'll break out of the inner loop. Okay? And then what you're going to do is you're going to swap the pivot that you have saved off, right? So I should be, when they have crossed over, right? I should be right in the middle, right? So now what you want to do is you want to take the pivot which is supposed to go in the middle, right? Because everything above the pivot is on the right, everything below the pivot is on the left, so the pivot has to come there. So you're going to do this swap, which is going to interchange
4 and 7.
4 and 7, right? So we got 4, then 7, okay? And then you're going to return j and I plus 1, okay? So you're going to return, say that the first partition ends here, and the second partition starts there, okay? So what that means is that you're not going to actually go back and do anything to that, right? Because obviously the pivot is already in the right place, right? You don't have to do anything, right? So you're going to do quicksort recursively on these two halves, right? And if you do that, well, ultimately, these two will get swapped. So when all is said and done, you'll have sorted list, right? So once again, in the case of quicksort, the only complex part is partition, right? Once you understand how partition works, the rest is easy, right? Okay, so we went in detail through how partition works, but after that, it's quite simple. The rest of the discussion on the rest is quite easy. Okay, so so could we have changed this to less than or equal to instead of less than? Would that be all right, or would that break something? So let's think about this, right? So our goal is to make sure that in the left partition, right, every element in the left partition should be less than or equal to the elements in the right partition, right? That is the only condition we need for us to be able to combine without any additional work, right? So that means we could change this to less than or equal to, and it'll be fine. And we could also change that to greater than or equal to, and that'll be fine. Okay? As far as correctness is concerned, right? But there is actually a good reason why it is a less than. Okay? And that reason is that in cases where, let's say, consider a list which consists of all equal elements, right? You can have you can be asked to sort an array where all elements are equal, right? So what's going to happen if it's less than or equal to? So what you're going to do is, if, let's say all elements are equal to p, then here you'll advance I all the way to the end of the array. So which means that the partitions will always be n and 1, right? So you'll create unbalanced partitions in those corner cases, right? And you know that in quicksort, that when you have unbalanced partitions, that causes quicksort to have quadratic time complexity, right? So we don't want that. So the point I'm trying to make is that I told you in the very first class, don't try to, don't tell yourself, I know the algorithm, I can write it, it'll work. Most of the time, it'll seem to work, but there will be some problems if you haven't really thought through, such as this one. So, if somebody thinks, so, so the significance of using less than versus less than or equal to is quite solid, and something that we are bound to forget. Okay, so so once again, coming back here, so the partition returns the end of the first half, the end of the first partition, and the beginning of the second partition, right? So you're going to sort from L through the end of the first partition, and then L2 through the end of the incoming partition, right? So that's why we have those two quicksort calls. Okay? Any questions? So we won't argue about correctness. I think at least you get a sense of why it works, right? So we divide it up, and then you put the pivot there, and then you can independently sort the two halves, and then you'll be done, right? So now let's look at the runtime. Okay? So what happens is that you have quicksort calling itself personally, except that in the case of merge sort, we are able to say both are n by k. Right? Here we don't know. Right? Wherever I and h happen to cross over, that determines what is the size of the first partition and what is the size of the second partition. So we can say, let's call it, let n1 denote the size of the first partition, and n2 denote the size of the second partition. And then we can write the recurrence P of n equals P of n1 to P of n2 plus the cost of doing the partition, which is n. Right? So now we don't know how to solve this because unless we are told what is n1 and n2, we can't solve it. Right? So let's consider various cases. Let's say we have a balanced split. So n1 equals n2, then that becomes n plus 2 times P of n by k, right? This is the same as the merge sort recurrence, so it's an n log. So let's say we have a totally unbalanced case, n1 equals 1, n2 equals n minus 1. Okay? Then the master theorem will tell you O of n squared. But if you don't have to use math theorem, you can also see that E of n equals n plus E of n minus 1 equals n plus E of n minus 1 again it's the same way. And so, right? So this is n plus n minus 1 plus n minus 2 so on. So that is the sum of 1 through n. So that's order of n squared. So you can see that if we get unlucky every time, then you have O of n squared. Right? So